Hello students, you all are warmly welcome. Here we are going to present you another lesson regarding grade 12 chemistry. It's under the first unit, it's the fifth lesson that what we are going to present you. So students, here we are going to present you regarding quantum model of the atom. So it's including quantum model, we are going to continue explaining how to write those electronic configurations of those atoms. Students, when you check for this lesson content in the competency, it belongs to the competency 1, which explains uses electronic arrangements and energy transactions in determining the nature of matter. Competency level 1.4, it's there, states the ground state electronic configuration of isolated means gaseous atoms and ions. Okay. So, then when you check for the subject content there, you could find that out the maximum numbers of electrons in sub-energy levels. We are going to find it out what sub-energy levels soon. So, wait, be patient. Students, it's principles and rules relevant to the filling up of electrons. It's under that we are going to talk about Hund's rule, Pauli's exclusion principle, its Aufbau principle and its deviations in higher atomic numbers. So, it's regarding electronic configuration of those atoms. Then students, it's further the subject content contains the ground state electronic configurations of those atoms. We are going to write, we are going to find them out, how to write those electronic configurations of those atoms. Then students, we would be writing the electronic configurations of first to 54th element. Okay, what's the quantum model? Hope you have kind of learned of or aware of those models already presented regarding atoms. Could you remember them? Students, it was Thomson's plum pudding model we initiated at regarding the atom, stating how those electrons would exist there. Within the atom, Thomson explained it's like a plum pudding. Plums that you find being immersed there in a pudding, those electrons you could find there inside of this atom being immersed in positively charged sphere or globe. But later on, it was based on that gold foil experiment, historical experiment made by Geiger Marsden, two students of Rutherford. Secondly, Rutherford presented the second model regarding the atom. So, it's because of the limitations we found there in the plum pudding model, earlier model. Students, the planetary model of Rutherford. But later on, we found out some limitations was there with the planetary model as well. Hope you could remember the last model we talked about was the Bohr's model. It was Niels Bohr based on quantum theory. So, he presented the idea of energy shells. You would have energy shells around the nucleus of the atom. Nucleus, what is the nucleus? It's the dot-like structure, or at the very mid you find all the protons and neutrons being there within the nucleus. It's the positive part of the atom. Then around the nucleus you would have those energy shells, what Niels Bohr said. So, it was the Bohr's model. So, Bohr said that you have energy levels around the nucleus, and those electrons are got filled, they are inside of those energy levels. Then students, this Niels Bohr's model, or let's call it energy shell model, was quite successful in the aspect of it could successfully explain those phenomena. What? It's the absorption and emission spectra of hydrogen. Niels Bohr could successfully explain how those absorption, emission spectra evolve of hydrogen only. Yeah? It's regarding multi-electronic systems. He also could not explain how those emission absorption spectra evolve there. Then he could explain nicely the reasons for having of large increments in successive ionization energies. When you talk about the successive ionization energies, it's all the times these electron removal would take further energy, further energy like that. I mean, the first ionization energy would be smaller than of second. Second would be smaller than of third, would be smaller than of fourth, like that. But there were some large increments. So, it's Niels Bohr could explain using his Bohr's model, could explain the reasons for having those large increments. But there were some limitations with Bohr's model as well. That's why the next model was presented. Actually, the next model was based on Bohr's model. So, it was developing Bohr's model only. The next it was presented this model, what we call quantum model. We are going to learn the quantum model here in this lesson, and we will call it the session. Students, Niels Bohr, though he could successfully explain how those hydrogen's absorption emission spectra evolve, there were some limitations with Bohr's models as well. So, in one aspect, we could say that according to Niels Bohr, an atom, he explained that you have energy levels there around the nucleus in a circular path. Then, according to Niels Bohr, an atom is a plate-like thing, but it is not, right? So, it's the three-dimensional spreading of those electrons was not there. The idea was absent there in the Bohr's model. Then, we further identify that when you talk about the hydrogen's emission spectral lines, you could find those spectral lines having different thicknesses. So, could not be explained using Bohr's model. As well as when you study those spectral lines in the presence of an electric field as well as magnetic field, those spectral lines could be found out that further splitting into component lines. That also could not be explained using Bohr's model. Those limitations were there. We call that, when it is under a magnetic field, when you observe that, we call that is the Zeeman effect. When it is an electric field, it's the Stark effects. So, this Stark effect and Zeeman effect could not be explained using Bohr's model. So, then with such limitations, they require further developments, further advancements regarding this model, Bohr's model. So, the question that presented on let's call it on planetary model presented by Rutherford. They asked, how does an electron revolve around the nucleus, not being spot on the nucleus. Nucleus is positively charged, then electrons are negatively charged. It's fair asking such a question. So, it was successfully addressed by Niels Bohr, saying, using that de Broglie's idea, a particle like electron, a smaller particle like electron could maintain particle as well as wave both properties at the same time. It's the wave particle duality that we have learned about so far. So, so far we have done those. Students, with that idea, Niels Bohr explained how does an electron would be revolving still around the nucleus, not being fallen on the nucleus. Then it was Heisenberg. So, Heisenberg, scientist named Heisenberg, presented the uncertainty principle. In Heisenberg's uncertainty principle, it explains that when you consider regarding an electron, when you consider it as an energy, it's we can't rely on, at the same time we can't find its particle. When we consider it as an energy, we can't rely on its particle behavior, as well as its, when we start considering an electron as a wave, it's we can't certainly say its particle behavior at the same time. We can't study the particle behavior at the same time. It's uncertain. It's uncertain. This is what we call the uncertainty principle presented by Heisenberg. So, then further it was Schrödinger, scientist's name. Schrödinger, he derived an equation as to predict the position that you could find an electron around the nucleus. It's using this Schrödinger's equation, they could find out, they could predict the position where you could have an electron there around the nucleus. So, it's the most probable place around the nucleus that you could find an electron out there could be named as an atomic orbital. It was named as an atomic orbital. The probability is 95%. So, the idea, with the idea atomic orbital, they could start predicting where these electrons you could find around the nucleus within an atom. So, then students, they started seeking for the places those electrons are there within the atom. Okay. So, with the atomic orbital, the concept of atomic orbital, they found in the very first shell around the nucleus, in the very first shell of the atom, you could find out an electron in a spherical region. So, the most probable place you could find there around the nucleus as it's a sphere shape. So, with the word sharp, it was named as a sharp means S atomic orbital. Students, then it was the very first atomic orbital found out from the very first shell. It was only one atomic orbital was there. It's the 1s. In the very first shell, you have spherically distributed region, that electrons distribute in a spherical region. It was called S atomic orbital. Then thereafter, when let's learn it in simple way. When the scientist named Pauli explained that, when he explained you could have an electron within an atomic orbital maximally being 2. Its students, maximally you could find it out 2 electrons within an atomic orbital. Any atomic orbital, the maximum number of electron would be 2. It would be 2. It's further we are going to find this out. We call that exclusion principle, Pauli's exclusion principle. We are going to find it out further in advanced meaning. We are going to talk about quantum number sets. One electron could not have same, let's say not one electron, 2 electrons could not have the same quantum number set. Is what we are calling the Pauli's exclusion principle. The simple idea of Pauli's exclusion principle is you can't have more than 2 electrons there within an atomic orbital. Then students, it was a spherical region that you could find an electron there within the very first shell. So, maximally it's 2 electrons. Therefore, in the first shell you could find that maximum number of electrons that you could ever have been 2. It's 2. Then students, let's go ahead with the idea of atomic orbital. When you check for the second shell, so it's already you have the first shell bearing maximally 2 electrons, and in the second shell again you have a spherically distributed region carrying maximally 2 electrons. Then it is a s orbital. So, this is the first shell is having s orbital, then in the second shell also you have similar spherical orbital, another orbital. So, it is 2s, let us call it 2s atomic orbital. Then students, it is not only just a s atomic orbital, it is when you have one of spherically distributed, there was another atomic orbital found there within the second shell in this manner. So, when it was found with a shape, they started calling that a p atomic orbital. So, with the word principal, it was named as p atomic orbital. The electron distribution could be found out being there in this region, within this region. So, it was a p atomic orbital. The shape was named as dumbbell shape. Then it was not just one p atomic orbital. It was such three of dumbbells could be found out. When you state them in a Cartesian plane as x, y, z, 3 axes, this is one of dumbbell, then this is the second dumbbell, this is the what? It is the third dumbbell. So, they spread there around the nucleus within the second shell, it is perpendicular to each other. Those 3 dumbbells you could find out being perpendicular to each other. So, this is the idea. Students, it is in x, y, z 3 axes, those 3 dumbbells could be found out being perpendicularly distributed. So, those got the same shape. It was those all 3 dumbbells were equal in shapes. So, then those together were named as the P subshell. Earlier, within the first shell, it was just a one of spherical shaped atomic orbital you could find. Then within the second shell also we found such a sphere. It is a S, it is the 2s. Now, you have dumbbell shaped atomic orbitals perpendicular to each other. There are 3 such dumbbell shaped atomic orbitals you could find there out. So, together you could call them 2p. It is 3 of p subshells. So, it is the 2p's, 3 of p atomic orbitals, it is the 2p subshells. Those alike atomic orbitals together named as one subshell. So, students, they found out atomic orbitals having the same shape or similar shapes. They categorize those atomic orbitals as one subshell. So, we now know 2 different shapes. One is spherical, other one is dumbbell shape. So, we know, therefore, we know 2 subshells. What are the 2 subshells? One is a subshell carrying 1 atomic orbital, spherical, 1 atomic orbital. Other one is the 3 of dumbbells carrying 3 of dumbbell shaped atomic orbitals. It is the p subshell. Within the second shell, you could have S and P, 2 subshells. Therefore, it starts the idea of subshells with the sense that you have atomic orbitals there within the shell. So, having equally shaped atomic orbitals, we call them subshells. So, in the very first shell, you have one subshell only carrying 1 atomic orbital, it is the S subshell, then therefore, we call it 1s. Then within the second shell, you have 2 atomic orbitals, it is 2 subshells having spherically shaped one atomic orbital and 3 of dumbbell shaped atomic orbital. All the atomic orbital orbitals is it would be, you could call 4 atomic orbitals. It would be 3 alike in shape are dumbbell shaped and 1 would be spherical. So, you have 2 different types of subshells. It is S subshell and P subshell. So, it is 2S and 2P. Then students, it's what would it be regarding the third shell? Let us find it out. When you talk about the third shell, it's you have 1s, 2s and 3s. In the third shell you have 3s atomic orbital as well. Then you have 3p, 3 of those dumbbell shaped atomic orbitals being there in the third subshell, third shell being 3p subshell. So, you have 3s, 3p, 2 different subshell. Additionally, it's you have another subshell. It's you have 5 of atomic orbitals there within that subshell. So, they could find out another differently shaped atomic orbital. It was a double dumbbell shaped one. With the word diffuse, they named that as d atomic orbital, and they could find out 5 of such d atomic orbitals being spreaded within the third shell. Then students, when you check that, it's when it is regarding x and y axes, you could call it dxy. When it is x and z axes, then it is dxz. Similarly, dyz. Then when it's you could find going along the axis, so we call that dx squared minus y squared, and finally it's through the z axis, you could call it dz squared. So, there were such double dumbbell shaped atomic orbitals, 5 of them, altogether named as diffused d subshells, d subshell. Okay. So, in the first shell you have 1 subshell only, it is 1s. In the second shell you have 2 subshells are S and P, 2s, 2p we could call them. So, in the third shell we are having 3 subshells. So, it is S, P, D. S is carrying 1 atomic orbital, P is carrying 3 atomic orbitals, and its D is carrying 5 atomic orbitals. Each atomic orbital could carry maximally 2 electrons. Therefore, students, when you check back for the very first shell, you could find 1 atomic orbital being there. It's a S atomic orbital, spherically shaped, so carrying 2 electrons maximally. So, the maximum number of electrons you could find there within the first shell is 2. Then when you talk about the second shell, you are having S and P, 2 subshells. Then S is carrying 1 atomic orbital which is spherical, and P is carrying, there are 3 atomic orbitals which are dumbbell in shapes. So, then altogether it is 4 atomic orbitals. Each atomic orbital could carry maximally 2 electrons. So, with that sense, we could say that maximally it is 8 of electrons you could find there within the second shell. Okay. With that sense, let us go to the third shell. When you talk about third shell, now you have a new member, new subshell being added. It is the D subshell carrying 5 of double dumbbell shaped d atomic orbitals. So, then when we talk about the third shell, students, we could find that out. It is within the third shell, the maximum number of electrons you would get. Could you find it out? Could you imagine? You have 3s carrying maximally 2 electrons. It's you have 3p carrying maximally 6 electrons. It's you have new member 3d carrying maximally 10 electrons. So, students, it's the maximum number of electrons could be kept there within the third shell is 18. So, it's I could show those 3d atomic orbitals, those 5 of 3d atomic orbitals in this manner, but it's you shouldn't worry, you won't require to draw them, it's quite out of our syllabus. I am just showing you. So, it's anyway we need to know what is the shape of s atomic orbital and what's the shape of p atomic orbitals, but not d. Anyway, it's just I'm just showing, so it's you don't bother about drawing these shapes of d atomic orbitals. Then shall we go to the fourth shell? Then students, it's we are going to find a new member there within the third shell. So, fourth shell, we already talked about the third. So, the new member is the F subshell. It's a F atomic orbital, it's we are not going to draw that for the reason it's quite complex in shape. So, it's you are going to find out 7 of atomic orbitals, we call it fundamental. With the word fundamental only, we name it as F atomic orbital. There are 7 atomic orbitals you could find within the F subshell. When it comes to fourth shell is having 4s, 4p, 4d and additionally it's 4f. It's 7 of such atomic orbitals you have, we call, when we come to the name of the shape, we call it, it's a complex shape you are having. So, it's SPDF, those subshells you could find out within the what? Fourth shell. So, then having another 7 atomic orbital being added there, it's S is carrying 1 atomic orbital, P is having 3 atomic orbitals and D is carrying 5 atomic orbitals, finally F carrying 7 atomic orbitals. It's the number of atomic orbitals, you add them up, could you? It's 16 atomic orbitals you could find there out. So, each atomic orbital could carry maximally 2 electrons. Then students, what's that? 16 into 2? It's 32. So, you could have maximally 32 electrons there within the fourth shell. So, these are the shapes of F atomic orbitals. It's you shouldn't bother about drawing their shapes, I am just showing you. Then students, it's next thing is when we fill those atomic orbitals with electrons, means actually it's we are going to find it out, electrons they are being filled into those earlier it was told as energy levels. But now we know within energy levels actually what we are having are atomic orbitals with alike shapes we call subshells. Within shells we have subshells carrying those electrons. Within subshells we have atomic orbitals having those electrons. Therefore, it's we need to know how those electrons exist there within the shells. In the shells, those are there in subshells. In the subshells, those are there in atomic orbitals. Okay. Then students, when you check how those electrons truly exist, actually it's before finding out or before talking about their electronic configurations of those atoms, in nature atoms exist means they did exist for all over the means all the time periods, means they were already there, those atoms. It's us, it's just us giving or naming those concepts as you have atoms, you have electrons there, you have protons there, you have neutrons there. It's us started naming of the nature. So, then atoms, they do not care whether we are having a concept, whether we having a theory or law or something like predicting where their electrons truly are. They are just having those electrons within those atoms. They do not care our concepts. Therefore, it is unfair calling that electrons, filling of electrons they are inside atom. They already have those electrons. It is just us. It is our intervene only, that we are going to name about atoms, that how those electrons get filled inside atom or something. It is just for our easy study, or to study them easily. Okay. You just simply understand, it is just because of us we are talking about an electronic configuration. Students, it's when we check for how do those electrons arrange there, or spread there, or structuralize there within the atom, in which atomic orbital, in which direction the spin is, in which subshell now those electrons are, in which shell that you could find those electrons. It is our concern only. So, to make them easy, the study, we are calling that electrons get filled inside those atomic orbitals in the subshells, in the shells. It is just us. So, we call them, we name them as the electronic configurations. Students, therefore, we are going to find it out. We are going to talk about their electronic configurations of those atoms. Okay. So, what we are next going to do is talking about how those electrons get filled inside those atoms. In that aspect, we need to know these things, that you have mainly 4 different subshells. Its first shell is carrying one subshell only, it is 1s. Second shell is carrying 2 subshells only, it is 2s, 2p. And the third shell is carrying 3 subshells, 3s, 3p, 3d. Fourth shell onwards, even 5th, 6th, 7th, 8th, any other, are carrying s, p, d, f. They all are having those 4 subshells after 4th shell, including 4th shell. You could find that out. Its SPDF subshells are there within those shells. Okay. So, with that idea, we are going to consider the electronic arrangement there within each shell, within each subshell. Okay. So, we are going to find this out. Students, do you think that when we fill those atoms with electrons, as it was there in the Bose model, in the Bose model we filled electrons as first we completed the first shell, then we completed the second, then after third, fourth, fifth, sixth, next, like that. Now, it is not shells only we are having. Is that then is that the same, that electrons are got filled inside those shells, inside those subshells? Actually, it is not. Students, though you have shells energy getting increased in the order of 1, 2, 3, 4, its subshells energy is not got increased in that manner, exactly in that manner. Okay. So, subshells would be following an order. It is a certain order you are having there. I am going to show you soon. So, it is the Aufbau principle, or we call it build up principle, that students, you need to know this. You need to know this, that electrons get filled inside the subshells. It is in the increasing order of subshells energy, not the shells energy. We call this the build up principle or Aufbau principle. It is the Aufbau principle or build up principle. What is the build up principle? Electrons get filled inside atoms in the increasing order, or let us call it ascending order of subshells energy. Subshells energy. Okay, it's we are going to find out what's the ascending order of subshell's energy, and we are going to fill electrons inside those subshells. So, it's what we call filling of electrons or electronic configurations. Okay. Then it's I could show you this. Hope you could still remember that fact, students. It's we found that fact out. You found that shells there around the nucleus. You found first shell, then after second shell, then after third shell, then fourth, fifth, like that. So, it's Niels Bohr explained it nicely. You have energy getting increase in the when it goes away from the nucleus, in the increasing order of this number. Let us call it the quantum number. So, it is the first quantum level, second quantum level, third quantum level, fourth quantum level, or in other words, first shell, second shell, third shell, fourth shell. So, when it goes away from the nucleus, you would find energy getting increase, as well as the gaps between those consecutive levels getting decrease. When you check for the gap here between first and second, and gap here between second and third, and the gap here between third and fourth, the gaps are decreasing, decreasing, decreasing. With that, when you split them means when you divide them, when you split each shell into its subshells it's having. Anyway, first shell is carrying one subshell, it's the 1s. Second shell is carrying two subshells, 2s, 2p. Anyway, so when you start splitting them, you make that sure you have 3 of 2p's. You have 3 atomic orbitals within that 2p. Therefore, when you check for this gap, it is 3 times, you get 3 times of that gap of energy, means this gap represents some certain energy. Then you get 3 times of that. That 3 times would be equals to the gap here. It's in this manner only those shells would have splitted into subshells. So, they get split at 2 sides. So, you had 2 subshells, therefore, it got split in 2 directions as 2s, 2p. So, let us talk about the third shell. Then students, it's when we go to the third shell, you have 3 subshells sp, d, 3s, 3p, 3d. So, when you split them, it's you could find here I have mentioned them in the here green color, in green. Then the gaps, when the gaps get decreased and when those shells get split further, could you find this point? Its students, when fourth shell gets split, its least energy subshell is the 4s. Its least energy subshell of fourth shell has gone down, further down, it's further less in energy than 3D. So, the point is 3D is carrying greater energy than 4s. This happens further with decrease of this gap further, and when those shells get split further. Therefore, I could tell this, students, it's not the same order of those shells that you could find their subshells energy get increase. So, you could find it out here, it's 1s, next is 2s, next is 2p, next is 3s, next is 3p, and next is not 3d, it is 4s. It is 4s you get that next energy subshell, not 3d. 3d you could find next. 3d is greater in energy than even 4s. It happens when those get split like that. Hope you could understand. It's very simple thing. Okay. Then students, it's therefore we could state that order of those subshells energy in a way like this. It's 1s, 2s, 2p, then it's 3s, 3p, is that 3d? No, it's 4s, then after only it's 3d, then after it's 4p, 5s, then after it's 4d, 5p, 6s, then after it's 4f, 5d, 6p, 7s. You might wonder whether I have by-hearted these all. So, it's you could have this order, this pattern of those increase in order of subshells energy, writing those subshells in the manner like it is first is carrying 1s, second is carrying 2s and 2p, its third is carrying 3s, 3p, 3d. You simply could draw them in that manner. It's 4s in the fourth, 4p, 4d, 4f. Then students, it's you could draw diagonals in a way like this, and you could link this to the other one, each line. So, in this direction only the energy get increased. Then it's we could explain that in a way like this. Students, when you draw as cutting those in diagonals, it's you could find the energy getting increased in this direction. So, it gives us the increase in order of subshells energy. Subshells energy. So, it gives you that pattern of these subshells energy. This pattern, it you could get there. Okay. Then you might wonder whether I have drawn them, right? It's you have the same thing drawn nicely. Okay. So, students, you might wonder whether we have any other method to get the same pattern. Okay. This is the pattern that subshells energy get increase. So, how could we get, without by hearting, how could we get the pattern? Is that we need to by heart that? No. Chemistry is not that horrible subject. It's students, we could easily get that pattern in a way. I am going to show you a simple way that you could get that pattern. Student, let me explain it in this way. Within one shell, it's you could have SPDF, those subshells. So, it's when we talk about S, I'll draw them in this manner, S, P, D, F. So, out of these within the same shell, S is the least in energy, then P, then D, then F. Okay. Then you start mentioning them, those subshells within each shell in this manner. You write all the subshells found in the first shell, it's 1s. You write subshells, all of them found within the second shell, 2s, 2p. You write those all the subshells within the third shell, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5s, 5f, those. Shall we call that the normal order? Then students, you start filling those electrons inside subshells in the normal order. Means you first fill the first found subshell is the 1s. Maximally you could fill 2 electrons there. If you have further electrons, what you could do next? Then if you have already finished filling one subshell, you check for this, whether what's the last filled subshell? It's a S. Whether you have a low or subshell, further subshell having lesser energy than of that. Last filled one was S. So, then when you check for any further subshell having lesser energy than S, do you? No. It's you don't have any subshell having lesser than S. Then you continue filling electrons in the normal order. In the normal order, you find next is the 2s. Then you fill 2s completely with 2 electrons maximally. If you have further electrons to be filled, you check what I have filled last, it's 2s. Then check whether you have any lesser energy subshell than S. No, you don't. Then you continue fill in the normal order, fill in subshell in normal order. After 2s, you would have 2p to be filled. Maximally, you could fill 2p with 6 electrons. You fill 2p with 6 electrons. Then, if you have further got electrons, it's you are lucky, then you have more electrons, right? They are within the atom. Okay. If you have further electrons got to be filled, then check for the last filled subshell. What's the last filled subshell there? Students, it's P. Then check whether you have any lesser energy subshell than P. Do you? Yes, yes. It's a S. It's a S. Then you do that. It's a S. It's S of next. Again, it's for the last time you have filled 2p. So, completing means after filling completely 2p, you check for any lesser subshell than p. It's a S, S of next. So, it's S of next to 2 is 3. You start filling 3s. You fill completely 3s with the maximum 2 electrons. Then afterward, if you have further electrons to be filled, you check whether you have any lesser energy subshell than S. No, you don't. Then you continue filling it in the normal order. So far, you have filled up to this. In the normal order, you would find it's been 3p. Then you start filling 3p. After completing 3p, you check whether you have any lesser energy subshell than p. Yes, you have. It's a S. S of next. After 3p, it's you fill 4s, not 3d. That's the point. Okay. After filling 4s completely, you check whether any lesser energy subshell than S. No, you don't. Then you complete those subshells, fill in electrons in normal order. In the normal order, you have skipped 3d. Now you go there and fill that 3d. You fill 3d with maximally 10 electrons. Then after, if you have further electrons, this doesn't end. If you have further electrons, you check whether you have further electrons, whether you have further lower subshell. It's lesser subshell than D. Yes, you have. It's P. P of next. P of next means it's 4p. You fill 4p. After completion, you check whether you have any lesser energy subshell than P. Yes, you have. It's S. S of next means it's 5s. In that manner, you could find this order. So, it's an easy way. I have not by hearted that order. So, I have just followed that order in my mind, my head. So, then students, you also could get the order easily. Shall we start filling electrons there? You would be impatient now filling of electrons there in the subshells of those atoms. Let's start filling. Okay, let me show you. You have those elements starting from the atomic number 1, 2, 3, 4, 5. It's hydrogen, lithium, hydrogen, helium, lithium, beryllium, boron. So, students, you have got 1 electron, you fill it here. So, you have got 2 electrons, you fill it here still. You have got 3 electrons here, you fill it here first, then you have 1 remaining, you fill it here. You have got 4 electrons, fill 2 here, then remaining 2 you fill here. you have got 5 electrons, you fill 2 here, it's another 3 remains, 2 here, another 1 remains there. So, in that manner you could keep filling. So, it's I randomly would take one of them. So, it's oxygen I will take. It's you are having 8 protons as well as 8 electrons there if it is electrically neutral. Then students, it's you fill 2 here, 2 here, another 4 it remains, you fill 4 here. So, you leave others empty. Then let us randomly take another one. I will take phosphorus having 15, the atomic number. It is having 15 electrons. How could we fill 15 electrons? It is in this manner. 2 here, 2 here, 6 here, it is 10. So, then it is 2 here, 12, another 3 it remains, you fill it here. That is what 15 electrons you could fill. So, students, I will take one randomly there. It is potassium, let us take. It is 19, the electronic configuration. So, following the Aufbau's principle, I could fill those electrons, 19 electrons there as 2 here, 2 here, 6 here, it took 10, another 9 you need to fill. So, it is 2 here, 12, then another how many? 7, then it is 6 here, another 1 remains. According to the Aufbau's principle, in the increasing order of energies in subshells, what you get next is not 3D, it is 4S. Could you remember? It is 4S. Let me show you that. It is 4S, 4S. Here, it is 4S. After 3P, it is 4S, then only. After 4S only, it's 3D. There are 4. Then students, you need to fill the electron remaining not to 3D. It's but on 4S. You leave this empty. That's how you could follow filling of those electrons. Then students, here in this lesson, we focused on the quantum model. What's the quantum model regarding atom? We found out earlier in the Bose model, we found out shells, energy shells. Then in quantum model, further we found out there are atomic orbitals. So, alike atomic orbitals called a subshell. So, you have subshells in the shell and then atomic orbitals carrying electrons. So, maximally you could have 2 electrons within one atomic orbital. It follows one certain order. It is the increasing of energy of subshells when you fill those electrons. It is what we call build-up principle or Aufbau's principle. So, we started filling electrons. You keep filling electrons. So, you need to know the filling of electrons up to from first to 54th element. So, we need to know the electronic configuration of those first 54 elements. Okay. Then, I made the introduction part, how to fill electrons there inside those subshells. So, you keep filling. Let us find it out in our next lesson, how those, there are few deviating, how those get deviate from the normal filling order, Aufbau's principle. So, we are going to consider the electronic configuration of those elements as well as ions there in our next lesson, as well as we are going to consider the quantum number sets. Okay, students, hope you have understood these few simple things, ideas. Those are very, very simple few ideas I have presented here. Okay, we are going to wound up here. Students, goodbye.